Welcome to Exam 3. Angular kinematics. We didn't do a lot of that, just one class. Velocity analysis, acceleration analysis of rigid bodies. Here's about the location where it is on the equation sheet. Here's old exam problems from the United States Coast Guard Academy at New York. Some of these were actually problems. Some of them were augmenting problems. Here we go. So this is where they said, hey, we ought to add some more problems. So you just start picking problems out of the book and to add some more practice problems. So some of them, and then here's some extra ones that I found from other places that I'm prepared to answer. So we could do whatever you want. But I would say the subcategories should include, in terms of things to be prepared to be able to do. We have angular kinematics, which could be a short problem. Sometimes I might incorporate a little bit of angular. I'm not going to emphasize angular kinematics just because the other problems take so long. Adding one of those problems on there just makes the exam longer, and I have enough stuff I want to cover. But for velocity analysis, I think the camera's right here. I think the microphone's right on that. I think so. For the velocity analysis, that has vectors, vector math, three diagram method, and instantaneous center of rotation. And there's a chance I could ask for a triangle, but I won't ask you to solve something by triangle, but I might go draw the velocity triangle after you're done with the problem. Acceleration analysis, that too could be done by the vector math or three diagram method. I'll probably ask three diagram method. Most of the time, not making any promises on anything I say right here, but most of the time, I will give you the angular velocities that you need in the acceleration analysis so you don't have to do it again, because you already will have figured it out in another problem, so why ask you to demonstrate it twice and just take more time. And then the subcategories would be general motion of a rigid body, crank slider and or slider crank, and then the dreaded 4-bar. So here you go. Those are the topics covered on Exam 3. I'm taking requests. Please don't ask for Freebird, because I might go at no charge. So. See, Freebird is a song by Leonard Skinner, who's not from Alabama, even though they sang the song Sweet Home Alabama. They're actually from Florida. And for whatever reason, at some point in the history of that song, when someone says, hey, we're taking requests, some jerk in the back screams, Freebird! And it's a running joke. So if you want to be in on the joke, someone says, hey, we're going to play one of our favorite songs tonight. You got to yell, Freebird! It's a running gag. Even if you're like at a rap concert or something like that, just any live show, if there's like a little pause, don't even have to wait for a prompt. Just yell Freebird, and you're going to be in on the joke. This long-standing joke, Freebird. And when I'm in a solo acoustic, if someone says Freebird, I play it. Just to torment them. All right, so I'm taking requests, not Freebird. What would you like to do? I'm not going to enter flashcards. So here's me like roulette. Just go stop. You can do a 4-bar. How about that one? That one might be too hard. What do you think? 4-bar's a lot easier if there's like if that link right there was if this link was the one that was driving, it would be a lot easier than if it's the one that's not driving with the unknowns. Just because the angles get screwed. So that one might take a long time. It'd be a terrible exam question. It's not too bad. We still have that problem with that other bar right in there. So this right here is technically, well, this is a velocity analysis. So we can do a velocity analysis actually pretty easy with a 4-bar. So what do you say we do a velocity analysis? Let me go back to this one, even though we could start this one. Let's do a velocity analysis of this bar. See if I can find it in the. So I don't have to read it. Might be one of the ones where I go, I didn't like this one. I wrote a ton of these out. Oh yeah, this one. Wrote this out. Okay. So let's go to here. So the angular velocity and angular accelerations of bar AB are 4 radians per second and -6. So they're showing an arrow that way, but they mean the other direction. Determine the angular accelerations of bars B, C, and C, D. And you have to do a velocity analysis of this anyway, so we might want to start that. And we might make an abbreviated start with the acceleration analysis just to see what we would do. But it is going to be a little hairy when it comes to the unknowns right there. So let's get the camera going. Let's see if the camera works. There she is. Camera time. Camera time. Let's see. I do this weird thing where I'm looking over my shoulder all the time. Yeah, that way. All right. So here we go. This is Bedford and Fowler problem 1796. And it looks a little bit like this. And let's see. That thing appears to be, so like, let's put in the distances right here. This is 2 meters. Like that. And this is A. And what they're measuring it down is they're measuring, here's 1 meter, here's another meter, and here's another meter down there. And let's see, I think this right here is 1 meter to kind of the center of that. That's 1 meter, not down to scale. And then this is 1 meter right here, and then there's another meter right there. So this is one of the base points right there for this thing, and it goes up and it meets right here, I think. Yeah, it looks right. So here's the center line of it. And then this guy, that should be at a 45-degree angle, but I didn't draw it the right way. And its numbering is, or lettering, I guess, A, B, C, and he is D. And this thing is rotating that direction at omega AB, and it's going this way at alpha AB. And let's see, the givens are omega AB is equal to 4 radians per second, and alpha AB is going in the direction I'm showing at 6 radians per second squared. And so the lengths, let's see, did I work out the lengths? The length of LAB is 2 meters. LBC, where'd you go, LBC? I'll write you down anywhere. You would think I would have written that down somewhere. I got you. Okay, I see what I did. It's 1.414 meters, and LCD is 2.236 meters. the angles that we want to get right here, this is 45. I'll call that theta C. It's not really fair to call it theta C. I'll call it that way. We'll just. I'm just talking about from horizontal. This one right here, call that theta D. So theta C is 45 degrees. Theta D, where'd you go, theta D? 26.56 degrees. So we could start with doing our ICR. And you got to be careful with the way you drew this and the way you're looking at it. Here's another peek at what the actual one looks like right here. If you were to extend this line, you would see that it doesn't go to there, right? So your eyes might be drawn to making the ICR that point right there. But if you were to use your straight edge and look at there, you can see that it's actually longer. ICR actually comes out over here. I did this on my iPad originally, so what you're seeing right here is on my iPad action going on right there. So I didn't have like a straight edge when doing the thing. But so that's where your ICR is, right? So remember, you just want to extend the links on a 4-bar, and where those links end up, those will be the ICR, because the velocity has to be perpendicular to this link that's connected to ground. And I should also mention, sometimes I think I forget this. I want to remember that the only place that we can use an ICR for, really, in practical terms, is the link that's translating and rotating, which is this guy here in the middle. These other two, that one and this one, they're just in pure rotation, so we don't need an ICR for them. We just need it for this. So we can redraw that piece right there. And I recommend doing that instead of trying to get all your lengths on top of this diagram right here that just clutters every damn thing up. So this ICR is, this length for the ICR. And by the way, we know that the velocity is coming this way, so we can even just write that out right away. Here's our VB, which we'll find here in a second. Okay, yeah. And anyway, you can draw this guy out. There's our ICR. This length right here is the one we just found. That was the LBC 1.4 in here. This angle, even though it doesn't look like it, should be 45 degrees. Right, because this one is 45, so this one must be 45. That's like that parallel thing right there. Right? This one, this should be the same as what we could call theta D. Right? That should be the same angle as this. And so that ends up being 26.56. So from that, we could get what this other angle is going to be, and I'll just call it something, just to give it a name. So we have 180 minus 45 minus our 26.56. And so that angle I didn't find it. So I did it a different way. I think I used, I see what I did. This way right here is better. I like this way better. So we're going to go 180, 45 minus 26.56 minus, so we get 108.4 degrees. And so what we want is RB with respect to ICR
and RC with respect to ICR. And while we're here, there's going to be our omega BC is going that direction because we're pinned right here, and that goes that direction. So this isn't going to be a pretty line because he's in the wrong damn spot. We can make a velocity, and that's one over here. Here's our VC. It's right there. So if this is LBC, we can do our law of sines and find, so here's the known one right here. So let's go that one first. So we go LBC. I don't necessarily need, I think it'd be quicker if we just put numbers in there instead of putting the symbols for the stuff. So the thing I want to get first is going to be the RB with respect to ICR. That's an unknown. We're going to divide it by the sine of the angle that's across from it. So that's going to be the sine of 108.4. That's going to be equal to, this is a known length, so we'll put him in there, 1.414. And that's across from here. So that's the sine of 26.56. And so RB with respect to ICR is, according to what I have, it's going to be 3. Right? So if I did this correctly, it'll be 3. So if you're playing the home version of the game. But I bet because of some amount of round-off error, especially of the small angle, I bet it turns out to be a little off. Yeah, I got it more than just a little off. I got it quite off. I got 3.11. So let me double check my everything. 1.414. So I had this 1.4142 on my page. And this angle, 26.56, what I have on there. Okay. And you never know. Let me double check my 108. I could have messed that up. 180, 45 minus, and then the 26 point. You said 57. Me too. All right, so 108.4 and change. I'll take the sine of that. I think I'm supposed to multiply. I might have divided. 1.4142 times, and then 26.57 sine divided. Yeah, I get this one. I get 2.99995 now. So 3. I might have just hit something wrong in my calculator. It happens. But it also could have been because of these little round-off thingies. It's surprising how they propagate, how quickly they do. So going down below 4 sig figs, will give you way more often.
You always talk about having a certain amount of sig figs. I know whenever you do your problems, you always have like 3 zeros at the end. Should we just be doing that always?
I'm trying, I'm not taking points off for that, but I'd recommend it a little bit, just as a... Yeah, I just think it's a good habit to kind of you're communicating that, I didn't round off anything.
And we've got those 9 lines. Should we always just go up to the next number, or should we just do 9 now?
Well, my thoughts are most of the time it's fine to default for in between steps of putting as many sig figs as you feel like doing, right? I think I've seen people that just go crazy and they'll have like 10-digit significant figures, and I don't think that's necessary. But the problem will arise, and I think we've already seen it in ME370, where we had the curved beam thing, where we did the eccentricity of these two things, which just means it's the difference between these numbers, and the numbers are so close to each other that if you round down to 5 sig figs, you're still left with, and you subtract them, you're left with only 2 sig figs. So you might as well go for, the extra thing, because you end up dividing some things by that number, and it has a real big effect on the results. So you can make a blanket statement, but there is a sort of it depends kind of aspect. Here, we go, we're almost certain that would have been 3 inches, and I found it in a different way. I just went ahead, and by the way, it's law of science. You could get around this by breaking triangles down into sub-triangles a lot of times, and make them into 90-degree triangles. You could break the thing apart, and it's not that, I actually kind of preferred doing it that way and forgot all about law of sines and law of cosines, but you can do it. It almost feels more like more creativity to break the thing out of triangles.
Yeah, breaking the thing down is just giving flashbacks to high school geometry.
Yeah. Some of those flashbacks we could get flashbacks. Yeah. So one thing I was thinking maybe I should have done, and you can do sometimes, is to march through these links, right? So before I got to this spot, I might have wanted to do a link A/B analysis there, and get a lot of things out of the way. Like first, some of the things that we could get out of the way is we could find out what this velocity is going to be. So VB, and I'll just write it next to the thing. It's going to be omega AB times LAB, or I could just write out the numbers in here. You could tell by the context of what it's supposed to be. So that's going to be 8, and we could, like here I am, like you're saying, Kyle. I'm putting the extra zeros in there because, I don't know, I kind of got into a habit of doing it. And then you could also, while we're here for the acceleration, find the acceleration of B in the y direction, or you could call this the tangential one if you wanted to. Alpha AB, LAB. So we get our 6 times 2, or 12 meters per second. And then you could also get this right here, at the acceleration of B in the x direction of omega AB squared LAB. And this is 4, so that's 16 times 2, so it's 32 meters. Oops, I forgot the second squared, per second squared. All right, so this is sort of an aside because we needed this VB, so maybe I'll put a thought bubble. I just like the thought bubbles. It's like it's floating in a cloud. So now we got this right here, so we can find omega BC by taking VB that we just calculated, divided by R, B with respect to ICR. And so that's going to be 8 divided by our 3. And some mortals would be able to do that in their heads, and I'm not one of them. That's 2.667 radians per second. Now, a sensible person would have already figured out what our C with respect to ICR is, but I totally forgot to. So let's just keep writing it down here in our stream of consciousness approach to things. It's kind of fun for some people, but not everyone. We'll go sine of, okay, so opposite from this one is our 45. And it's still going to be our 1.4142 divided by the sine of 226.57 RC with respect to ICR. Another time and space, Dr. Deal wrote down that was 2.236. But let's see what kind of mistakes I can make now. 4142 26.57 sine divided, and then multiply it by the sine of 45. And I get 2.236. Oh, look at that. Me and him, we agree. So we can find V of C. Find that guy. So VC is going to be equal to that omega BC times RC with respect to ICR. So we end up with, where'd you go? 2.667, 2.3, 2.236. And so 2.666666 times, you get 5.962 meters per second. Yeah. Close to it. In my other one, I got 2.9628. So there's a little round off error buddy going on. While we're thinking about it, we could bypass, and probably if we're going to be asked a 4-bar when it comes to velocity analysis, what we really, our goal is to find out what the angular velocity of this thing is. All right, so we could go ahead and find that out right now, pretending like that was our goal. So length CD. And we have a velocity that is coming up this way. All of a sudden I got hungry. I wish I had eaten some. VC. So we know it's this direction because of our ICR analysis. So here's our omega CD is going that direction. So VC, well, I could just write it this way. I don't have to write that out and write it again. Go omega CD. It's going to be VC over LCD. Please stop me if anything doesn't make sense at any given point. I'm sorry if I'm going too fast. My mind is just like, oh, this problem should take this amount of time. And we can go as slow as you'd like, right? So we found this length up above. So if there's anything by any chance that you it's like, man, I don't see why you did that, or wow, I'm lost. Just slow me down. I should say that in class more. Just slow me down. Slow me down. I don't think it's a song. And we get, ooh, this is interesting. I guess that kind of makes sense. Sometimes these things are symmetrical in a sense. I got 2.66, and there's another 6. But it could be a 7. I think it's probably, I think of some amount of symmetry. I'm trying to think. I guess I can kind of picture that. Maybe it has a lot to do with the 45-degree angle up in the other one, maybe. I don't know. I don't know how to explain it geometrically. I'd have to think about it longer than I feel like thinking about it. But one of the things that we get out of this while we're here, save ourselves a little bit of time, is that we could get the normal acceleration. Even though we don't know the tangential acceleration, we can get the acceleration of C with respect to B, D, not B, sorry, in the normal direction. And one of the things that's messed up with the problem that doesn't help us in the acceleration analysis is the fact that this thing is at an angle. Kind of prefer to have problems that aren't that way. But we can go omega CD squared plus L, not plus, but times LCD. Supposed to be keeping track of that. LCD. So 2.667 squared times 2.236. And so 2.236. 2.66666 squared times. Ooh, man, I am hungry. 15.90 meters per second squared. That's what. Not yet. I mean, it's at this. We're in a normal direction. We could break this. There's several ways to keep track of these things. But one method I have used before, and I've stopped using it, is to always break, as soon as I see this, to break this into X and Y, because I'm going to use it later. But I kind of like, it's a lot of stuff to keep track of. And that's actually, I think, one of the hardest parts of the acceleration problems. There's often a lot of stuff to keep track of. It's a good skill set, though. Keeping track of a lot of stuff as an engineer. So much stuff to keep track of. Gets overwhelming, so staying really meticulous about stuff so you can keep track of things is it's not something we're born with. We have to develop it over time. So here we go. Here's the ugliness. So this thing is at a 45, so I don't have to worry about making it a 45. It would be nice to be able to use the correct 45, if you will. But doesn't matter numerically, but a certain amount of keeping track of crap kind of helps. All right, so we're going to have, if you'll recall, we had an acceleration down this way, an acceleration to the left here at this joint. So here is to the left, and here is down. And I'll call AB X, AB, Y. And we're going to put that on each of these, on both of these, not the one on the left. And I probably should have drawn these whole thing maybe just a little bigger. Would have been nice not to get things run into each other. There's no really reason to label that one. This is the one that we kind of. But I'm trying to be thorough. All right, so this is the one I know fully, so that's going to be my reference. And this is the one I want to find out. I don't know. Okay, so I see what I did on my previous one, and I might go ahead and post this, what I've written before, but I think this is the way to go about. But this is too long for an exam, this next thing. It just takes too much time. I would go like this, I think. I would go ACX, ACY, right there. So just assume positive right there. And then this one, we will know this value. So we'll put a little leader over here and go A, and this is going to be C with respect to B. And the normal, which is going to be omega BC squared LBC. And you can find this value right here. Sometimes I will have let that thing carry through all the way, but we know that it's 2.667 squared, and that the length of this is 1.414. Give it another sig fig of 2. So 2.666 and square it, 1.414. 1.4142 times. So I can't tell if this is an artifact right here, but you get 10.05 and then a 2 next to it. But I think it's probably a legitimate value. Yeah. And previously I got 10.056. So we'll just leave it here, recognizing that we might have some round-off error. And this way right here, I almost always go positive direction for guesses. So that would make this acceleration of c with respect to b in the tangential direction, which is alpha bc times lbc. The angles in here, like I said before, they don't really matter. But if you were going to do it correctly, it would be this 45 degrees and this 45 degrees. It doesn't really matter. It's 45 degrees, either way. But so this whole diagram right here is valid for this equation, or is used with this equation, the whole point of the thing. Acceleration of c with respect to b in the tangential. I usually go tangential first. Try to be consistent. Tangential direction plus acceleration of c with respect to b in the normal direction. So write them out. Acceleration of c. So our problem is we can't solve these like directly straight out. We have to kind of play a little bit of a game. It's going to be equal to negative this guy right here, which we found out to be 32. Plus, we don't know this one, but he is in the, we've guessed in the positive direction, so we go alpha BC, and I'll put the actual length in there, 1.4142. And now I got to remember, don't forget, remember, got to put the sine of 45 in there. People forget that all the time, to put the angle next to the sine or cosine of the angle. And this one I've written as this way, so I'm using sine for that, which is at least correct up to the diagram. And then this is also positive, and that's going to be 10.05 of this part right here, and it's going to be the cosine of 45. So it wouldn't hurt us to go ahead and find out what these values are. 45 times cosine, and that's positive, but gets to this, so we get 32, get subtracted out. So we're going to have a negative 24.89 plus, and I think this 45 is going to act in a, I think it's going to equal to 1 right there, right? If you multiply the sine of 45 times 1.4142, yeah, it should be equal to 1, right? So it's just alpha BC. Acceleration is c in the x direction, so go there. All right, so this, we might call that equation 1, because we have these two unknowns, so we'll put a pin in it. So acceleration in the c direction in the y is going to be equal to, let's see, this is going to have a negative ABY, and that value we found out was 12 earlier. And then we're going to have this guy again, and he's going to be negative as drawn, times the length, 1.4142, times now the cosine, but of course it didn't really matter. And then this is still positive for x direction, y direction, excuse me. So it'll be plus 10.05, but now it's going to be the sine of 45. So we'll rewrite this out, reduce it down. So we get 10.05, 45 sine times, and subtract out 12 from it. So we'll have a negative 4.894, call it. And then this is negative, minus, and then this times that should be alpha BC. We go 2. 2 equations and 3 unknowns, so we have to come up with other equations for this, and the place to do that is from right back up here. Once again, we have to make an assumption. I will guess that alpha CD is going in that direction, and therefore the assumed direction of AC with respect to D tangential is down and to the left. It's going to be alpha CD times LCD. So the method I would go about to try to resolve this, there's a couple different things we could do. We could actually do a coordinate transformation, and that might actually be the easiest, most. This is not like on the exam, right? This is too long, so we wouldn't be doing this. But if you were going to try to resolve this, a coordinate transformation might be the most methodical way that you would go about doing this, right? That you would go from a tangential and normal right here to a I and j to an x and y, right? So we have the normal en, I guess, and the et that way right there. And so what we would write up for the acceleration of c, we would write that in the tangential and normal direction. Writing up for here in the tangential direction, we'd have alpha CD times LCD, which is 2.236 ET. And that's the positive direction as drawn right there. And then plus, we would have 15.9 EN. And then, as you'll recall, our coordinate transformations right here, that angle right there is our theta D. And so, therefore, that, too, is our theta D, theta D, theta D up there. So, the coordinate transformation, if this is I and j, and this is et and en, we'd say in the I direction, it's going to be a negative sign. Do you agree with that? Recall doing this? All right. And then in the j direction, it should be a negative cosine. In the n direction, it should be a positive cosine. And it should be a negative sign. Right, because we're going downwards from here in the j direction with our en. So AC is going to be equal to, we'll go the tangential first. I guess we could do the mixed first. We'll go for the I. Yeah, it'll work out. Theta CD times 2.236 times the negative sine of 26.56. All right, so that gave me the I from here, and then plus 15.90 times the cosine of 26.56. And that should give me the I plus, and then I'll go back to the thing again, alpha CD 2.236 times negative cosine 26.56, and then plus 15.90. Wow, somebody really, I don't know what he was telling me. 15.90, and keep it together. All right, negative sine of 26.56. J. So, working this through, acceleration of C is going to be 26.56 sine 2.236 times. All right, so that's almost that right there almost comes out to 1. It's 0.99979. So that's like 1. So you get, but it's negative. So you get a negative alpha CD plus, and that's about 15.9, and we get to 26.56 cosine times, and you get 14, that is positive, 14.22, and that's the I plus, I'll do this again, and I gotta kind of wonder, no, probably not. Let's see what happens. 26.56 cosine 2.236 times comes out to 2. Isn't that boring? So you get a nice 2, and it's a negative 2. Don't forget the negative there. Alpha CD, and then this is going to be negative, so minus 15.9 and 26.56. And I'll take the sine of that and multiply, and we get a 7.109 J. All right, so these are really two equations, right? We could set these equal to these others, right? We have two equations and two unknowns now. We have this one, so we could say that we have negative alpha CD plus 14.22 is going to be equal to negative 24.89 plus alpha BC. We could put either one that we want to right now. Let's go ahead and move this guy over to the side, so you're going to end up with 14.22 plus 24.89. Let's add them together. So we're going to go 39.11 minus alpha CD is equal to alpha BC. All right, then do the same thing for over here. I'm going to go negative 2 times alpha CD minus 7.109. It's going to be equal to this equation up here, negative 4.894 minus alpha BC. So I will Go ahead and just put this alpha BC from up here into here. So alpha CD equals 7.109 plus negative 4.894 minus 39.11 plus, because it's minus alpha CD. So that's going to come over here and go to the other side and be a negative 3. So let's see, we go 7.109. We go minus that. Boom. It's in my calculator still. Minus 4.894. Boom. So I get a minus 36.89 on the right-hand side, but I have a minus 3. So I divide it by 3, and I get alpha CD is equal to a positive 12.23. Was it 12.2 or 12.3? 12.3 radians per second squared, and now you plug this probably back into this one, so we'll subtract that from 39.11, and we get an alpha BC of also a positive 26.81 radians per second squared. Wicked frickin' long problem. I know. But if you could do this, you could do the ones on the exam, because the ones on the exam can't be this hard. They're just impossible to do. But this is, the skill set that you're building up, really, that's useful for continuing on in education, is just keeping shit together, just keeping track of these details. But if you go back, and the satisfying thing to do at the end is you said, well, we had 12.3 and 12.8. Woo, look at that. Or 20, what did I say? I said the wrong thing. 26.81, 26.8, 12.3. We did it. We did it. Just like Dora the Explorer. We did it. We did it. Swipe or no swiping? That's what I was to say. Now after that, I broke you. Okay, let's do one that's more fun.
The issue is made of math mistakes somewhere.
Hey, yeah, but finding it though can be like that reinforces some of those things, right? You know, it's like there's a tripping point. There's a tripping point for me, but that problem took us a freaking hour to do. So that's not like a good example, is it? But you do one like this, right? You do this. Let's do this one right here using vector analysis and ICR, and let's time both of them. Right? By the way, time yourself. You time yourself. So just feel comfortable enough. Don't beat yourself up because of the time when you're still trying to get the thing down. But pushing yourself, as long as you don't break yourself, it can be a really good test-taking strategy here. So let's take a look at this problem from Bedford and Fowler. You know, the thing that you'll really hate, I could tell you that I actually have equations, like a single equation, not a single equation, but a routine for some of these that you could just solve. There's like gimmicks and things that you can. I also have MATLAB codes that you can just plug the numbers in and get the right answer. Doesn't that make you just kind of like, why don't we just use those? Why would we ever need to do this? Because we're not learning this. There's no way we're learning. We're learning to keep track of shit.
I think that's a big question for like in the future when we go to a workshop. Yeah. Why would we need to do it hands-on when we have stuff like MATLAB? What other things do all the companies will have those?
Well, not you don't necessarily know that every company will have MATLAB, but
even then,
but people, the professors think that. Everybody has Excel, Yeah, most of, and honestly, if anybody could plug and chug it, why are they hiring you? Right? What they're hiring you for is the problems that aren't already done. So yeah, what we're going to have to do is, if you had to do a task that was involving that kind of thing, yeah, put it together, assemble the thing together. But most of the time, yeah, it's hard to say. The projects are usually not this. This is just a representative problem. You learn the representative problem. You learn to think your way through a representative problem, and then when you're given a problem I can't think up yet because it has yet to be answered, because that's what they're going to hire you to do. You're going to have the mental acuity to be able to, and that was a great word. I just pulled that right. Just pulled that right. Acuity. You're not as impressed with me as I am with me. My ability to pull out words that I didn't know I knew. My daughter's always asking me, like, how do you know that word? I'm like, I have no idea. Where did you get that word? It just came up somewhere at some point. All right, so this one too is the annoying 45, but I guess we'll just go ahead and do it. This does appear from the information to be a 45. This is not a 45 right here. Something like that. I think I want to exaggerate it down because their dimensioning on this makes it. Are we timing this? I forgot. Maybe we should draw the problem first and then start the timer because it wouldn't be fair. So I've already done this once before with ICR.
And all the questions on the exam were open, so use this method.
Yes, because I'm testing you on that method. And I want to be consistent with how I grade, although my grading has evolved, as I think I've mentioned before. I'm at a higher level of grading now. This is 4 inches, and this is 10 inches going across. And this is 3 inches from there to there. And then this is 4 inches, so that's going to make that a 45. And the labeling of it is A, B, and C. And our known is going to be 6 radians per second. So, let us begin. Reset. Boom. Oh, hey. She ordered takeout at AJ Noodles Bar. Oh, Andrew did that. That was a nice daughter. What a sweet girl. I don't know what that AJ's Noodle Bar is. Well, let's do this instead. I think I'm going to start out with my position vector of B with respect to A. Easy enough. We're looking at B from there, so that's going to be 4I plus 4J. We know when we get to here, we're going to need our C with respect to B. So we're going to be looking to the right, but down this time. So that's going to be 10I plus negative 7J. And we're given that omega AB is equal to a negative 6K. So we'll start out with the velocity of B is equal to the velocity of A plus omega AB crossed with R, B with respect to A. But we know that that's going to be 0. Velocity, B right there, is going to be -6 times, I'll just go ahead and distribute it, because we have that, so we could might as well, 4K crossed I plus -6 times 4 K cross J. We know that's a positive J, and that's a negative I. So our VB, and there's a negative and a negative, so those are going to go away. So we're going to have 24 I plus negative 24 J. And that makes sense, right? Because it's going this way, down, and it's 45, so that it makes sense that they're equal to each other. Now we could say that the velocity of C is going to be equal to the velocity of B plus the velocity of C with respect to B. Some things that we should maybe note: that this velocity of C has to be VC in the I direction. Also, by the way, I'm going to erase this. I meant to, that velocity of C with respect to B, of course, we know that that is also omega BC crossed with RC with respect to B. So that BC is equal to omega BC K. So velocity of C is going to be, okay, let me actually replace that with the speed of C times I. It's going to be equal to 24I plus negative 24J, and then that's going to be plus omega BC times 10 K crossed with I plus omega BC times negative 7 times K crossed with J. And that's going to be J, and that's going to be negative I. So now we can collect the things together. Good strategy is to pick J because we know it's going to be 0 on the left-hand side. So we get negative 24. And then here we're going to have this one. It's going to be plus omega BC times 10. So we just found omega BC is going to be equal to 2.4 radians per second. We could plug that back into I. So we'll get VC is equal to 24. There's that negative and negative right there. So it's going to be a positive omega BC, which we just found, 2.4 times 7. And so 2.4 times 7, 2.4, boom. We get is 16.8. And that was not what was asked as part of the thing, so we could actually have, if that was the plan, we would have already been done with the thing, but we could go ahead and look at our counter. And oh yeah, 24, sorry, thank you. So what is that, like 30.84? 40, thank you. Anyway, that was a 6-minute problem. Boom. Can you get that done in 6 minutes? Can you? Try it. You think you can do it? I mean, I'm just, just have a conversation. Do you think? You could if you did like 2 or 3 problems, right? Go for speed, get that done, boom, knocked out. Because that's just bang, bang, boom, right? That the vector math thing, you almost turn your brain off when you get the thing done. Just get used to it. Look for the pitfalls. Look for the things that you don't have to think very much. All right, that's one reason why I don't like it. But I want you to be able to do it. But 6 minutes, the rest of the exam. Speed. Seen Rocky 2, where he makes him chase the chicken. Yeah, it's a great movie. I like Rocky 2 better than Rocky 1. Rocky 1 was a better film in terms of you didn't expect him to lose. Oh, spoiler alert, sorry. If you haven't seen Rocky 1. In Rocky 2, you give she wakes up from the coma. Oh, spoiler alert, sorry. And she goes, win. And then they play the music, dun, 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 dun. And then Burgess Meredith goes, what are we waiting for? Like right, it said, I said the direct quote. But then he makes him chase the chicken, catch the chicken. And he goes, that's speed. And that's a hand gesture that I've only watched the movie 1,000 times. Anyway, so let's go on to the other one. Let's go ICR. Let's see how fast ICR goes. It's a fresh piece of paper, but we won't redraw the whole thing. Same problem, different method. This is good. This is how we prepare for an exam. In every class that you take as an engineer, every class, do this. I swear to you, success is around the corner. Let's start. Boom. There are some things in this. We need the length of LAB, which is just going to be the square root of 4 squared plus 4 squared, which I don't know off the top of my head, but that's going to be, what, square root of 32? I think so. Feel free to tell me I'm wrong. I'm wrong a lot. Kind of get used to it. Don't mind it no more. And that's not true. Bothers me like crazy. I don't mean to be a liar. Let's see. Let's get the length of BC while we're at it. I don't know what that noise is. Something that was telling me something. It shouldn't be my email, because I don't think my email's on there. So that's going to be, what, 10 and 7? Yeah. 10 squared plus 7 squared. So 149 square root, boom. 12.21 inches. Let's find out what this theta C is going to be. It's going to be the inverse tan of 7 over 10. And boom. We have 34.99 degrees. Now we can check out what the link AB velocity analysis is. It's 45 degrees. We got 6 radians per second. Sorry. So here's our VB equals 6 times 5.657. 5.657 times 6. Boom. We have 33.94. And we don't need any more of that. So here I'll take my ruler and come down here. I think it's going to be a doozy. And at 45, let's come at 45. Remember that we could do our first quick one over here, by the way, for our ICR. Just real quick, we could go, oop, has to go up there. This one has to extend up there, right? So ICR is off the page. Way the hell up here. Yeah. We'll fudge it a little bit for this one. Like that right there. Here's our VB. Here's our ICR. And we can see that we're going to have our omega BC right there in that direction. So our velocity of C is right here. Here's our RC with respect to ICR. Here's our RB with respect to ICR. It's supposed to be the with respect thingy. Okay, let's take a look at our angles right here. Here is our angle that we just found here a second ago that I called theta C. We can see that this is 90 minus theta C. Right here is our theta C, and right here is the, I guess we'll call it theta A, which is the 45 degrees. This is actually the hard part, so maybe even though I'm going against the clock, we should slow down just ever so slightly and double check all of our angles and our mindset on how we got the angles. It's one of the things to practice, probably, focus in on when it comes to ICR. Where are the angles? How do I figure out that? Is the geometry, going back to geometry. This is an angle we found, and we know that this is 90 degrees, so we subtract it from 90. Here is also that same angle right there, because this is a line that's going across perpendicular lines. And then this one right here is just an extension of this angle right here, which was theta A, 45 degrees. We need this angle up here. We could call it anything we want, but we know that it's going to be equal to 180 minus, actually, I would actually probably maybe find this one first, that the 90 minus theta C is going to be 90 and 34.99 minus, so 55.01 degrees. So I don't have to write up that long damn thing. And I'll go 55.01. And then I might actually find out what theta A plus theta C is going to be. And so that's just going to be 45 plus 33.99, which I should do in my head, but I'm not going to. 78.99. Boy, yeah, might as well make that 79, huh? So that's going to be minus 78.99. So that phi or psi or whatever the hell it is, add them together, 180 minus, I must have messed up. That says it's 46 degrees. I feel like that's 45. That should be 45 degrees right here. So I screwed something up along the way.
Shouldn't be 79.99?
Yeah, basically 80, huh? Let me double check on this one. Because I must have written something down. That's a 34.99, which is very damn close to 35, right? But it is 0.7 and inverse tan of that. Yeah, that's correct. And then, but I go 90 minus that.
It's 56.06, not 55.01.
Really?
Minus theta C. Theta C. I was going off the BB, yeah, that's not right. I was looking at the BB, not the theta C.
Okay. But this one I'm pretty sure about right here. I just without doing any holdovers right here, that was the value of the thing. No. Yeah, theta C. Well, no, I go. If you go 0.7,
I think you added something like 44.98 plus 45 should be 79.
yeah, 79.99. Sure. And then 90 minus the 34.99. Okay. Yeah. Yeah, so this should be 45. But even if you look at this for a second, you could go, oh, that has to be 45, because that right there is a 45-degree triangle right there. Anyway, this is where I've messed up my whole clock thing, but that's okay. So I'm going to go law of sines again. It's probably the most, without. I could also break this down into triangles. In fact, you just saw me break it down into triangles. I would often do that, where I would find out what this leg is going to be based on this, and then I would find out that leg from there. But if I know this distance right here, the one that I need first is RB with respect to ICR, and the angle opposite of that is going to be the 55.01. And that's going to be equal to, I'm going to take this length right here, which I had up above as 12.21, and divide it by the sine of 45. So I find RB with respect to ICR, 12.21, 45 sine divided, and then multiply by 55.01 sine, boom, I get 14.146, I'll call it 5. And these are inches, right? Makes more sense to just go ahead and do the other one while we're here instead of doing it the haphazard way. This is the 79.99, basically 80. And then do this one again. Sine of 45. We get RC with respect to ICR, and so we have 12.21 sine 45 divided, and it goes 79.99 sine times, and I get basically 17. And now I can find omega BC by taking VB and dividing it by RB with respect to ICR. The VB that I got up above was 33.94. That's probably what I messed up somewhere. I might have, these numbers look too similar to me. Like a little bit of, call it non-permanent dyslexia. 33.94, 14.15 divided, and I get an omega of 2.398, which is really what the initial problem, well, it's got some more numbers after it, 6 radians per second, and I think that's what we got before, yeah, 2.4, so we got some round off error right there, 2.4 is what we're looking for, which would come out right here if we round down. And then VC is going to be omega BC times RB with respect to ICR. So 2.3986 times, yes. I was daydreaming about the noodles. She tempted me with noodles. 40.78 inches per second. So what do we do? How do we do? Boom. 13 minutes because I talked about too much. Messed around with the angles too much. So the vector math was a lot faster, huh? This has some good visual aspects to it. I don't know.
Visually, this one's easier to take.
And you could use them kind of in conjunction with each other. You could also do the velocity triangles if you wanted as part of this. You could go. Actually, the 3 diagram method works best with the velocity triangles, I think, because when you break the thing down into here and this one has to be horizontal. So we get down like that, and then we'll assume omega BCs. Now that way, here's your V, and this is the C with respect to B, C with respect to B. So here's your V, B, and then VC is like this. You can assume in that direction. So when you go to the velocity triangles, the answer has to be right there. Whoops, didn't do a very good job of that because I got to give myself room. I didn't do a great job of my angles right here because I think that has to be an angle, and that has to be an angle. So that's and so this is a smaller angle to the thing right here. So. So this is the VC, and this is the VB. No, that's the VB, C with respect to B, sorry. And this is the VB. So that'd be your triangles right here. And this is a 45 right here. And this would be the complementary angle of your 34, of your 34.99. This right here would be the 55.01 in your velocity triangles. You see that? A lot of places they use the triangles for everything. There's a certain amount of justification for these vector triangles, by the way, especially when it comes to navigation. There's a lot of navigation that gets done by hand. And yes, you could plug things into the computer, but when it matters a lot, you also back it up by doing stuff by hand. So you will see on a ship, on a Navy ship, they still use charts. Yeah, you could do it in the computer, but they'll still have a chart table, and they'll still be navigating because you need to find a bunch of different information. People need to visualize it. And I think I could say that. Yeah, I think the navigation officer will still be able, and the people in his department or her department. And then still, with aircraft and that kind of thing, people will do the triangles. The triangles matter. And keeping those ideas, especially with relative motion type of thing. So. Still in use today, not displaced entirely by the computer. What would you like to do now? Go get noodles? I have to grade things and write a thermal exam. I've written it, but I have to rewrite it. I have to readjust it.
Is it possibly one for 47?
What's that?
Are you writing the one for size class that you're?
No. I'm just a proctor.
Yeah.
I'm just somebody that has to figure out a way to wake up and get here by 8:30.
The rest of the class.
I taught an 8:30 class for years. I don't even know what I'm teaching next semester for. Not 100% for sure. Only 3 people signed up for my mechanisms class.
I think I'm
You're signed up for my mechanisms class?
I think I signed up for a big class before.
Okay.
I'm not sure.
Well, that would be the class then, probably. No, ME 470.
Did you keep that 7 semesters?
No, ME 470. No, you signed up for 470. No. Yeah.
Oh.
This is a senior course. Mechanisms is a senior course. An elective.
Yeah,
It's actually these things, gizmos, doohickeys, and whatnots. And I think maybe people have enough scar tissue. They're just not going to take the class. I made a beer pourer last year. That was the project. Is we made a beer pourer. So we 3D printed it. It was lame. We're going to do better, cooler things. I'm going to make it like a 3D printing class.
What is the point of the class? Are you just making mechanisms, or is it more math?
We're designing them.
Okay.
We're using math and more complicated things to design them, but people rebelled against the hand calculations, so there's less hand calculations and there's more using the MATLAB things and the SolidWorks, and I don't know, it's exploring how to design. How do you make a gizmo? You want to pick up a beer and you want to pour it. How do you make a machine to do that? Could you do that if I said, hey, with what you learned at the University of Hartford thus far, could you make a machine that picks up a beer and pours it? And the answer is no, you couldn't do it yet. So that's why you take my class, because you have that very important function of picking up a beer and pouring it. They could do that, but somebody had to make that robot. You too. Okay, please.
Question. Are you catching up on that coding? I didn't see if you could. So,
I'm going to try. Let's see what my endurance versus noodles goes like tonight. You know, I don't need your guilt. I put enough on myself. But I'm going to use the Asaki. He says, he told me, and I don't know if he's lying, he said, I have not graded a thing this semester. He can't. He doesn't have any time. He's here throughout the middle of the night.
How about this with you, where you get the work and you kind of stack it up?
I used to have a grader. I had a couple times I had an overload where I had top four classes, and Cy, when he was department chair, gave me a grader, and my life was miserable because that guy was terrible. Like everybody hated him. At least everybody hated him instead of me. All right, I'm going to grade quickly. That's what I'll do. So you would like to see the homework? Okay, let's see.
I just had a question on the relative problem.
Yeah.
So the relative velocity would be with respect to C.
It's something like that, right?
I think that's the first one.
Well, the first one's a wheel, and it's got a thing in a slot. The first one's something like that. I just switched which thing was which, basically. So which one did I give it? This is the input? Oh, okay, yeah. Okay, so it's basically the same thing, right? So right there, and that thing, and that thing. Sure. Okay.
So that relative velocity of B with respect to C, is that just the velocity of B?
No. This is moving either towards it or away from B with respect to C.
Yes. Oh, so we have to restrict it.
It's getting shorter. That distance right there changes. You could even say that it would be B with or B with respect to C would actually be an R dot. If you were to say, hey, what's the distance of this? Is that getting shorter or is it getting longer? I can't remember. Which way did this one move, clockwise or counterclockwise?
That moved counterclockwise.
Yeah, so you kind of expect this, your gut, that this is getting shorter between these two.
Yeah. But isn't the mechanism of CB just going to follow whatever shape A travels? So at point B, it's just moving.
Okay, well, you'll go VB is going to be equal to VA plus omega AB crossed with RB with respect to A.
Yeah.
All right, we're okay with that? But then you look over here and you're going to go VB is going to be equal to VC plus omega BC crossed with RB with respect to C plus V rel, or I could just say VB with respect to C if I wanted to. Call this the rel. Because these are changing, this effective length is changing between B and C.
Because it's not VBC, it's the relative velocity of I don't know why my brain is just getting caught on
I got you.
VBC.
There's two unknowns, the magnitude of this and the magnitude of that. So you just want to set these two things equal to each other and then let the vector math work itself out. The only thing has maybe some amount of complications. I can't remember what angle that is right there. But you want to, this thing right here is going to be like, call it whatever you want. I could call it relative or whatever. But multiply it by whatever the thing is in the I direction and the V rel times whatever the thing is in the J direction. Aren't you glad I got rid of the acceleration part of this? It's like that long. It's like that. This piece of paper. It was this piece of paper long. In the typewritten one. So the other one was like this long. This one was like that long. That's all I asked you, as opposed to that one up there.
So glad you got rid of the self-utilization. Did you say that Coriolis wasn't?
Yeah, no. I just thought I'd figured that the Coriolis would be like helpful. It's just too long. It's just a long problem to ask.
Probably at least 95% of everyone in the class would. Thank goodness.
So I think though to have 95%, we'd need 20 students though.
Yeah.
Okay. You're just a relative, just a rough estimate. Okay, I'm just saying. So I don't know. My head just went to that though.
I'd say.
Is that wrong? Was that wrong on me? Okay, there you go. There you go.
Say probably all of it.
All the class. You good? All right. I'm going to go grade some things, but thermo has to come first because they have an exam tomorrow. But I already posted the solution, so we'll see. Just lay it on the floor. Ouch. Another successful video made.